Welcome to CSC 201, Lesson 3.1. A predicate is a sentence that contains a finite number of variables and becomes a statement when specific values are substituted for the variables. The domain of the predicate variable is the set of all values that may be substituted in place of the variable. So, for example, we're going to let P of x be the predicate x is a factor of 24, with the domain being the set of all positive integers, z plus. So we're going to write a sentence for P12, P9, and P of a half and indicate whether the statement is true or false. So P of 12 means I replaced the x with a 12. So in the sentence, we replace the x with a 12. So that means 12 is a factor of 24. And is that true or false? It's true. 12 is, in fact, a factor of 24. P of 9 says that 9 is a factor of 24, and that is false. 9 does not divide into 24. And P of a half is undefined, because 1/2 is not in the domain. 1/2 is not an element of the positive integers. Now, the truth set of a predicate P of x is the set of all x's in the domain such that P of x is true. Let's list the truth set for the predicate we've been working with, x is a factor of 24. So basically, we're just listing a set. So we'll use the roster method where we just put all the elements in curly brackets. We're just listing all the x's that are a factor of 24, all the x's that would make this statement true. Okay, so we've got 1, 2, because 2 times 12 is 24, 3, 4, 5 is not a factor of 24, but 6 is. 7 is not. 8 is. 9, 10, and 11 are not, but 12 is. And then 24. Okay, those are all the factors of 24. All right, the universal quantifier. Symbolically, we write it like this. It's like an upside down A, and it means for all or for every. You can read it either way, sort of depending on the context of the sentence. A universal statement is a statement of the form, for every x in D, Q of x. You would read this as, for every x in a domain D, Q of x is true, or for all x's in D, Q of x is true. Okay, it is defined to be true if and only if Q of x is true for each individual x in D. False if and only if Q of x is false for at least one in D. And if you can find a value in D that makes Q of x false, we call that a counterexample. So let's look at the statement, for all x's in Z, for all variables in the integers, for all x's in Z, x squared is positive. Is this statement true or false? Okay, so for every integer, when you square it, you get a positive number, true or false. So this is false because there is a counterexample. It's almost always true, but consider x equal to 0. Okay. If x is 0, and 0 is an integer, so we have found one x in the integers such that x squared equals 0, meaning it's not positive. Okay, so x is in Z, x squared is not greater than 0, so we have a counterexample. The existential quantifier, which is a backwards E, symbolized as a backwards E, it means there exists. So the root word of existential is exist. Okay, so this is the existential quantifier. An existential statement is a statement of the form, there exists an x in D such that Q of x is true. Okay, so It's defined to be true if and only if Q of X is true for at least one X in D. False if and only if it's false for all X's in D. Okay, let's look at an example. We're going to consider the statement, there exists an X in Z. So we're looking for there exists an integer. There exists an X in the integers such that the absolute value of X is less than or equal to 0. True or false? Is there an X whose absolute value is less than 0? No, but there is one that is equal to 0. This is true. X equals 0 is an X in the integers such that the absolute value of X is 0, which is less than or equal to 0. The quantifiers for all and there exists are sometimes implicit in a sentence, and it can take some thought to tease them out. For example, a math textbook might tell you that x plus 1 squared is x squared plus 2x plus 1. But what they really mean is that for all x's in the real numbers, x plus 1 squared equals x squared plus 2x plus 1. That this is true for all real numbers x. Elsewhere in a math textbook, you might see a problem that says solve 3x minus 4 equals 5. But what they really mean is show that there exists an x in the reals such that 3x minus 4 equals 5 by finding the x, right? Show that there exists an x such that that statement is true. So the quantifiers for all and there exists are sometimes not written down, and you have to carefully read and decide, are there quantifiers implicit in that sentence that you need to consider.